Hello everybody and welcome to this video on energy systems. Now, I have made this just after your mock exam. I know some of you before the exam were saying that you were a bit concerned about energy systems. Looking at some of the answers on the exam, I agree with that. That's clear. So maybe this will be a different look at it. Just a look from a different angle might help you. It's a video that's here that you can always look back at. Now, it's a bit of a long one. You will see, so look at the chapters. You don't need to watch it all at once. Go for chapter by chapter as you're trying to sort things out in your head. Please feel free to go on 1.5 speed, 1.75, whatever. As long as you can understand my silly accent, go for it. That's all great. But what I would say, with the time you buy yourself doing that, come back and watch it again. Remember the thing with the name at the party. You think you've got it and then you don't revisit it and all of a sudden it's gone. So even if you're thinking you've understood this at the end, it's well worth revisiting, and that's just going to solidify it in your head. So when you come across those questions, it's happy days. You've got a fairly good understanding of it. So watch it fast, but watch it twice is the advice I've got for you. Now, what are we going to do? We're going to work backwards from the cross-bridge cycle was fairly badly understood, I think. Obviously, it's a while since you've done it, and I get that. So we're working backwards from that, and then we've got some other stuff to add on at the end. So let's start with this stuff, glucose, and what we do with it. So that's our glucose. You'll notice there are 6 carbons there. So we take that glucose and we split it. Is my computer going to go slow here? There's our 6 carbons, and that's glucose. We split that into 2 pyruvates that have got 3 carbons. So from our 6 carbons, we've got 2 times 3. These things are called pyruvates. Pyruvic acid, there it is. See the 3 carbons right there. That is called glycolysis. Remember, lysis is the breaking apart. I think of that sword slashing things. I don't know why, but that's there you go. That's what we've got. Glycolysis gets our 2 pyruvates. Now, ATP, that energy currency. I'm afraid this is going to cost us 2 ATPs, this process, but good news, we're going to get 4 ATPs in return. So happy days, we are 2 ATPs up on the deal with glycolysis. Now, one of the questions was to talk about catabolism. So we've got metabolism and catabolism. Catabolism is the breakdown of complex molecules into simpler molecules, which results in the release of energy. There we go. That's what's happening here, isn't it? Now, they've got the breakdown of glycogen into glucose, but we could also go for the breakdown of glucose into pyruvate. That's another example of catabolism, a catabolic reaction, if you will. So, before we move on, this is something else that you're going to need to know, and you'll never guess how I'm going to tell you is the best way to learn it, but something like this into Anki, where you're covering one at a time and saying, what is that, and then revealing it, and yet that's going to help you. That awkward bit where you're trying to remember, that's when those memories are really getting laid down so that you can bring it back. So there we have an animal cell, and look, annotate the diagram of a generalized animal cell. Excusez-moi. There you go. There it is there. Something that you're going to need to know. So glycolysis has got us 2 ATPs. There's our cell. That's just a fancier drawing of what we were looking at before. And this glycolysis happened in the cytoplasm of the animal cell. We've got the nucleus there. There's a mitochondrion down there, a mitochondria, the powerhouse of the cell, which we're going to look at a little in a little more detail coming up. Cytoplasm was the glycolysis. We also got 2 NADHs. You don't need to know much about NADHs. There it is there, but essentially you just need to know it's an electron carrier. You probably won't even need to give it that name of an electron carrier. You need to know that it's a thing. NADH. If you want to give it some silly acronym for what NADH stands for, all the better to remember it. You know I love that stuff. Let's move on into the mitochondrion now. We have got the inner part there is called the matrix. Now, bit of an aside, actually, we have got here some lovely fat. Look at that, there is fat, and we're just going to look at the process of slashing that fat. You know, we've slashed it with that sword, must be lysis there. And fats are lipids, so what we're looking at here is lipolysis. Fats and triglycerides are broken down into, and we get glycerol and fatty acid chains. So lipolysis is fat giving glycerol and fatty acid chains. What happens to those things? Well, the glycerol, it goes into that glycolysis pathway that we've already looked at, but we also, remember, got those fatty acid chains, and they get broken down through beta oxidation. Good word to know there, beta oxidation, and from that we get acetyl-CoA, important stuff that we're going to look at later on as well, very shortly in fact. So fatty acid chains get broken down by beta oxidation, and that produces acetyl-CoA. So also, speaking of acetyl-CoA, we're going to take our pyruvate and we're going to get some acetyl-CoA from that in our second reaction, which can be called pyruvate oxidation. It can also be called the link reaction. That's it happening there. Again, don't need to know all the details of what's going on there. Essentially, we take our pyruvate, through the link reaction, we get an acetyl-CoA. Which is going to be handy later on. We also get 2 NADHs from that. Happy days, no ATP, but not to worry, this other stuff that we've got is going to come in handy in eventually getting the ATP, which is that energy currency. So the Krebs or the citric acid cycle is next up. We are going to take, in here we're going to have enzymes doing some work. Enzymes essentially just make the sparks happen. We've got these two people here, they're going to meet, there's going to be some wonderful reactions. The lady that's introducing them there, she's not involved in that reaction, she's just introducing the two of them. She is an enzyme. That is what is at work in the Krebs and the citric acid cycle. So we take our acetyl-CoA. Remember, lipolysis, with that fat we broke down into glycerol and fatty acid chains. Then through beta oxidation we got that fatty acid chain and we got some acetyl-CoA, which is what we're going to use here. We also got some through glycolysis. That glycolysis gave us pyruvate, and the pyruvate through the link reaction gave us some acetyl-CoA. So we've got this acetyl-CoA that we're going to spend in the citric acid cycle. Now, let's take a pause for a look at this question. We've got outline the process by which fats can be used to provide energy for this event, whatever event that was. Outline the process by which fats can be used to provide energy, essentially is what we're looking at as that question. So have we covered? Fats and triglycerides are stored in adipose tissue, used as energy in long duration endurance events. We've not covered that, but I think you knew that anyway, and there you go, you can get a point for that. One of your 4 points can just be, where are fats and are they used as an energy source? Fats and triglycerides are broken down into glycerol and fatty acid chains. Happy days, we've got a point there. That's called lipolysis. Remember, that lipo is the fat. Think liposuction, when people get their fat sucked out of them. The lipo is the fat, and that lysis is always the breaking down. So we've got lipolysis is taking fats and triglycerides into glycerol, fatty acid chains. Happy days, so far we're on 3 points. Glycerol enters the glycolysis pathway. Yep, point. Good. Fatty acid chains further broken down. Remember, that was beta oxidation. There's another one, and this gives us acetyl-CoA, which enters the Krebs cycle. Brilliant. We've got more than enough to get our 4 points there. Now, beta oxidation produces a high number of electron carriers used in the ETC, in the electron transport chain. Not quite covered that. Let's not worry too much about that. But what we will find out is that the high levels of ATP we get from the electron transport chain, we get high levels of ATP. We're going to find that out later on. There we go. So we can get, the last two are a bit, we've not quite covered them here, but we've easily got our 4 points for a question like that. Now, oxaloacetic acid. You do not need to, I might well even be pronouncing that wrong. You don't really need to know what that is. In fact, this whole thing, it's just kind of nice to know that this is a thing. It's not shrouded in mystery. It's a thing. You're not going to be asked a lot about this process itself. But we've got this 4-carbon chain. The acetyl-CoA has got 2 carbons. We put them together to get a 6-carbon molecule, which is citric acid, the stuff that's in lemon juice. We're going to take this on a little journey around the Krebs cycle. Reduction is loss, remember, so we're losing an electron. We're taking NAD+, we're getting NADH. We also get some carbon dioxide with that. We're going to breathe that out. We do that a couple of times. I'm going fast here because you're not going to need to know the ins and outs of this, but this is what's happening. We've got our ADP and we get an ATP back. Good. That's something that we're going to be able to spend on. That's our energy currency. Oxidation is loss of electrons. We've got FAD and we're getting FADH2. Happy days. And we've got our NAD plus into NADH again there. So what have we got from this? Well, we got 3 NADHs. There they are there, circled. We got 1 ATP. That's it, circled there. And we got 1 FADH2. Remember, our acetyl-CoA, for every glucose molecule, we got 2 acetyl-CoAs. So we can multiply these by 2. For every glucose molecule, we can multiply these things by 2. So we get 6 NADHs, 2 ATPs, and 2 FADH2s. There they are. Let's put them off to the side. That's what we have got so far from that 1 molecule of glucose. So I think it's time to do some sums. We've got our 3 processes here: glycolysis, pyruvate oxidation or the link reaction, and we have the Krebs cycle. Now, this is theoretical. Different people will tell you different numbers. In fact, whatever these numbers are, it's probably going to be fewer than this, but we need just an idea of the sort of ratio of ATPs that we're going to get. So we're looking for ATPs, we're looking for NADHs, and we're looking for FADH2s. ATPs, we got 2 in glycolysis, we got 2 from the citric acid cycle, the Krebs cycle, we've got 4. NADH2s, we got 2, 2 and 6 in the 3 reactions respectively, we've got 10. FADH2, we only got that from the Krebs cycle, so we have 2 of them. This ATP, we've got 4 of them. What are we going to do? Get it spent. Get some energy from that immediately, and very soon we will have a look at exactly how we do that. These 2 though, the NADH and the FADH2, that's onto the electron transport chain. Now, again, don't spend too much time remembering exactly what goes on here. I don't want this to be some sort of mystery about what is the electron transport chain. Isn't it a funny thing? This is what's happening with it. You're very unlikely to be asked the actual ins and outs of it. An atom, rather, has positive protons in the middle and negative electrons on the outside. You may well know this already. Just good to make sure that we know that. Remember the wonderful joke, I think I've lost an electron. Are you positive? Yes, he's positive he's lost an electron, because when he lost the electron, he's now only got 2 negatives on the outside, but he's got 3 positives, so he overall is positive. Let's take what we have got. We've got these NADHs and the FADH2s. There's our matrix, and this is going to be happening on the inner membrane, and on the membrane there between the matrix. There's our matrix there, there's our membrane, and there's our intermembrane space. So this is that membrane. There's our NADH down the bottom left there, and our FADH2 will go quite quickly, but essentially NADH offers up these 2 electrons. In they go. We're going to take some protons in there. These electrons are going to power this pump to put those protons into the intermembrane space. We've not finished with those electrons yet. They're going to go on to this other pump. The FADH2 is going to offer up some electrons, and they're going to get passed into this next proton pump, where we're going to take some more protons and get them out into that intermembrane space. There we go. Still not finished with those electrons though. Those electrons are going further along this chain. It's an electron transport chain. We're going to put them back into this pump, but this pump's going the other way. We want to get rid of those electrons now. How do we do that? We take an oxygen that we've breathed in and we offer that up. That oxygen is then going to take those electrons and it's going to take some protons. Now, what have we got here? We've got an O in the middle, and every time we've got a positive and a negative, that's 1 and 1, that's just hydrogen. So we've got 2 O's and we've got 4 H's there. So that means we've got a chance to make 2 molecules of H2O, water. So there we've got, I don't need to worry about that staff meeting, let's dismiss that. There we've got our H2O that we're going to breathe out. So we've gotten rid of that, and now we've got all of these protons in the intermembrane space. And we're going to get some diffusion happening here because there's a mismatch, isn't there? And they're going to go through what's called ATP synthase. Good to know about ATP synthase. As those protons go through, that ATP synthase is going to spin. We're going to offer up an ADP, and this ATP synthase is going to turn that into ATP. There we go. So it's quite a lengthy process, but we got our ATP from that. For every NADH that we put into this electron transport chain, we're going to get 3 ATPs. And for every FADH2, we're going to get 2 ATPs. So we're going to be pretty ATP heavy at the end of this. Let's just add that up. Let's have a little check. We have got our 4 already from ATP. Brilliant. Our NADH, we got 10 NADHs, remember, overall, but then we put them into the electron transport chain, and that multiplied them up by 3. Remember, for every NADH that went in, we got 3 ATPs. So we've got 30 ATPs from that. For every FADH2 that went in, we multiplied that by 2. It got 2 for every one of them. We put 2 in, so we get 4 from that, which gives us a theoretical ATP yield of 38. There's every chance that the mark scheme will tell you 36. Quite a few people will also tell you 36 is the number. I think you can even go as low as 34. Like I say, in reality, it's going to be lower than that. You're not going to get a question, is it 36 or 38, that the electron, how many ATPs can you get from one molecule of glucose? You're not going to get 36 or 38 as an option. That would not be fair. If it's going to be mid to high 30s, or like 2 or 4, and it's mid to high 30s is your answer. The electron transport chain is where you get most of these. So that's our molecules produced per molecule of glucose using these various systems. Glycolysis, we got 2. The link reaction, we didn't get any, but we got other stuff that was useful later. The Krebs, we got 2, and check it out, the big dog, the electron transport chain, is getting us, in this example, those 34. It is by far the winner, the big kahuna of getting ourselves those ATPs. It does take time to get them, so they're not immediately available, but it is by far the winner at getting us those ATPs, and that's a big thing to remember. What gets you the most ATPs? The electron transport chain. Okay, so remember, you don't need to remember all of that, but just so that it's not a total mystery to you, and so you've got some idea of what's going on. That's how we can get those ATPs from glucose. Now, we've got it, time to spend it. let's have a look what's happening in this cross-bridge cycle. Remember, we've got actin that is thin and the myosin that is thick. Let's take a closer look at these. The myosin has got these myosin heads, which are bound to the actin. Now, check it out. They're going to pull that along, a lot like pulling a rope with your hands. That's called a power stroke. Now, it's time for that ATP to come in. This is a little bit counterintuitive, because you would think the ATP gets used to do the power stroke. Like, that's when you're working, when you're pulling a rope, so surely that's the bit the ATP gets used. It's a little counterintuitive, because look what happens here. The ATP will attach to the myosin head, and that prompts the detachment of the myosin head from the actin. So the myosin head now, that ATP has told it, right, time to get off of that actin. So off it gets. Now is time for that ATP to break down into ADP and a phosphate, and that is going to release some energy. We've got our energy, and that energy is, most of that energy anyway, is going to go make those myosin heads go back and reattach to the actin in the cocked position. If you think of a gun for that cocked position, you cock the gun. The energy moves the myosin head into the cocked position and causes rebinding to the actin. So now that's with the actin, and it's time for that to start all over again. I did say most of that energy, because there is some of that energy is also used to transport some calcium ions back into the SR, the sarcoplasmic reticulum. So after that contraction, the rest of that energy will take some calcium ions off to the SR, the sarcoplasmic reticulum, for you. Off we go, and we're ready to start our process all over again. These myosin heads that are attached, we're going to pull that actin along. That's the muscle contracting. Then the ATP is going to come along. It's going to attach to the myosin head. That's going to prompt the detachment of the myosin head from the actin. Then it's going to break down and give us some energy. It's going to then, that's hydrolysis, that's the breakdown of ATP into ADP and phosphate, and that energy is going to drive the myosin heads back along and into the cocked position, attaching themselves to the actin. We're ready to go again. The rest of that energy is going to take those calcium ions off to the sarcoplasmic reticulum. So that is the cross-bridge cycle. Quite important, that little counterintuitive bit where it's the energy actually takes the myosin heads back and reattaches them. It doesn't do the pulling along. That's why, if you think about it, a dead person goes into rigor mortis. You know, dead people are often absolutely stiff. Their muscles are contracted because there's no ATP to move it back, to release that. So when there's no ATP, the muscles end up contracted. They don't end up relaxed as you might expect. That's that it's slightly counterintuitive part. So what have we got from that? ATP attaching to, so this is explaining the role of ATP. This was the question. ATP attaches to the myosin head and prompts the detachment of the myosin head from the actin. Yes, we got that. Hydrolysis, that's the breakdown of ATP to ADP, releases energy. Happy days. The energy moves the myosin head into the cocked position, causes the rebinding to the actin, and the energy is also used to transport calcium ions back into the sarcoplasmic reticulum. So quite tricky. I mean, you've got to hit most of them to get our 3 points. But hopefully, if we've got more of an understanding of what that looks like, we'll be able to hit that. There's the hydrolysis, there's the cocked position, and there's our calcium off to the SR, just to help you remember that. Next up, insulin. Let's just put this in here because this was another question. We have got, hang on a second, I've just got some people asking here. Hiya. You don't need the room?
Just to show him the room.
Okay, I'm just, thank you. Sorry guys, that was somebody looking into the room here. So we have got Insulin, how does it work? What's the deal with insulin and muscle contraction on glucose uptake? Here's the bloodstream. We've got glucose in there, and the pancreas is producing this insulin. The insulin is going to help that glucose into the muscle. Exercise is a stimulus for this. So exercise is a stimulus for skeletal muscle glucose uptake. So when we exercise, we stimulate the glucose uptake. Here's a way to think about it. You'll often see the key analogy, which is a perfectly good analogy. This is another thing I'm thinking of. If it helps you, great. If not, feel free to ignore it. Here we've got a little girl helping an old lady across the road. The little girl is the insulin and the old lady is the glucose. She needs to get from the blood into that muscle. The insulin, it's got the keys, it's going to let that happen. It's going to attach itself and let that glucose through. If the insulin wasn't there, if the little girl's not there with the keys, the old lady, she can still get across the road, but she needs to take another pathway. She's going to need to go over that bridge. So it can still happen that the old lady can still get across the road, the glucose can still get into the muscle, but without insulin, it needs to take a different pathway. Insulin helps that to happen. A bit more counterintuitive stuff here. When we exercise, it actually lowers the concentration of insulin in the blood. So it's not like you might think, oh, I start exercising, so my pancreas starts kicking out the insulin to make sure that this can happen. No, it lowers the concentration of insulin, but it's offset by the fact that there is increased sensitivity of the muscle membrane to the insulin that is there. So the insulin that's there, the muscle membrane is more sensitive to that, and that helps that glucose get through to the muscle. Sorry, 2 seconds, that's Andreas just coming. I'm just going to need another few minutes to make this, so I might be a little bit late. Send my apologies. I'm just finishing this off. I think it's up in the auditorium. Yeah, I think so. Sorry guys, that's that staff meeting that pinged up there. I'm going to be a bit late. Sorry, I don't know why this keeps coming through. So, how much does glucose uptake increase? There's a question. Well, it's going to depend, isn't it? It's going to depend on what is it going to depend on? Something about the exercise. Two fairly obvious things: the intensity of the exercise and the duration of the exercise. The more intense and the more the longer it's going on for, the more glucose uptake is going to have to increase. What else increases that surely will affect glucose uptake? What else is happening once we start to exercise? Our blood flow is increasing. So once we start to exercise, we've got more, the blood flow increases. So of course there's going to be more glucose gets across there. Sorry, this is going through again, it's my bad. Will the effect be seen before or after the exercise? It would be much more sensible if it was after. Before, we don't even know if exercise is going to take place. So after the exercise, this can also happen. Now I've got my computer breaking down. Here we go. There's a question. Outline the role of insulin and muscle contraction on glucose uptake during exercise. So exercise lowers the concentration of insulin in the blood. Good. Offset by exercise increasing the sensitivity of the muscle membrane to insulin. Happy days. Exercise is also a stimulus for skeletal muscle glucose uptake. Good. We've got that. The magnitude of the exercise increased is related to both intensity and duration of the exercise. Happy days, we've got that pretty much. Delivery of glucose and insulin to contracting skeletal muscle is increased during the exercise as a consequence of the large increase in blood flow. We've got that. Blood flow is also a thing. Remember that bridge pathway for glucose into cells is different to that induced by the insulin, by the little girl having the keys to get across the road. And the effect of muscle contraction intake persists into post-exerse to restore depleted stores. A little bit more on that later on as well. Maximum 2 for insulin or muscle contraction out of 3 though, so not too bad. So we've got to look at both of them. So I think though we could answer with all of them. Now then, last thing to talk about here, and then I'm off to that staff meeting. Again though, you don't need to look at all of this, remember. Oxygen debt, oxygen deficit. I just put this in because some of you were asking about it before. It seemed like maybe you're a little bit unsure of it. Here's a different way of looking at it. Let's see if it helps. We've got our sushi. You know these sushi restaurants where all the sushi goes on a conveyor belt? And it goes round and you eat it as you go, and then so some of the sushi is coming back here. Look, there's Mario, he's not even eating it all. He only needs 1 sushi per minute. This could also be a muscle needing oxygen, and our blood's going round, and it's nice and easy because there's more than enough oxygen to happen because we're not exercising. Then though, we up the exercise a bit, we need 2 sushis per minute. No problem, we're still producing enough for that. That's not an issue. We really start exercising now. Let's say we jump on a treadmill and start running, and we need 5 sushis per minute. We've only got 4 there. Hang on a minute, I'm going to have to get organised. We're not producing enough. Our chef is not producing enough sushi. We're not producing enough oxygen right now in order to supply those muscles. This was inspired by a friend of mine who's still a good friend of mine, but when he was at school, he used to, and this is an aside, but it's funny, so we'll go with it. He used to buy a bacon roll. You'd go through like a bit where you'd pick up your stuff, and he'd buy a bacon roll. He'd ask for a bacon roll from the canteen, and he'd take the bacon and he'd put it in his pocket, and so he would go and he'd pay for a buttered roll, and then bacon out the pocket into the roll. That's what Mario's doing here. He's got some sushi in his pocket. So while I'm getting organised, Mario is going to have to get that sushi in his pocket and get eating that, because I'm sorry, I can't provide enough for you just now. So take that sushi out your pocket and go for that stuff while I'm getting myself organised. What's the body doing to get itself organised? Well, we can put 3 on each plate. That would be the stroke volume of the heart can increase. And we can put more plates on so that he's getting plates more regularly. That would be like the heart rate increasing. These are the things that we're doing while Mario is eating that stuff from his pocket, because he needs to be eating that. If we're on a treadmill, if we don't have that energy, then we're going to go off the back of the treadmill. It's not like it's not an option. It's non-negotiable. We need to get that energy from somewhere, so we need to take it out of our pocket. Once we've got that, look, now we've got enough sushis to be going round. We're back in the game, and Mario can get back to putting some of that actually back into his pocket again as well. Let's see if this analogy works for you. I know it's a bit of a stretch, but let's have a look at a little graph here. Here's time. And there is our base metabolic rate. That's how much oxygen, when we're just sitting down, we're not doing anything, we still need to consume oxygen. As you sit watching this video, you are still breathing. You still need oxygen to keep yourself going. I'm going to give you a workout though, and it's going to look, or I'm going to give Mario a workout, and it's going to look like that. He's going to start working quite hard right away. That's why it's quite good to think of a treadmill like this. This isn't just something where we're just slowly jogging around the gym, getting faster and faster. This is, we put the treadmill on a speed, and boom, on we get. We have got an oxygen requirement that goes up right away. Body notices that and it says, hang on a minute, let me get myself organised, let me increase that stroke volume, let me increase that heart rate. But that takes time, doesn't it? You don't just jump on a treadmill and all of a sudden you've got 100 beats per minute. It's got to go up gradually. So this space here is where we're taking that oxygen, those sushis, from our pocket, from our reserves. We have to take them from our reserves while our body sorts itself out. If you look now, the treadmill has actually, we've gone fast and then slow again, and fast then slow again. So even though we're up to our requirement, then we ask a little bit more of it, and then a little bit less. So look, these bits here, we're filling our pocket again. Look, it doesn't just, the heart rate doesn't just drop down immediately once it stops getting difficult. And these bits here, we had to empty our pocket because we're getting asked too much. We had to put our heart rate up there, and potentially our stroke volume up if it wasn't already. Remember, stroke volume is not going to increase once we get above 120 beats per minute. That's our stroke volume, will be maxed out. Once we finish and we're chilled out, again, the heart rate doesn't just go back immediately. This is excessive post-exercise oxygen consumption. So once he's sitting in his chair there, still his heart rate's high, because he's got some he's got his pocket to fill, essentially, which we're going to look at that. Now, Luigi, turns out he's a lot fitter than Mario. Look at him, a lean machine there. He's fitter. So with him, that heart rate would drop down faster after exercise. The epoch wouldn't be as pronounced with him, wouldn't be as long with him. So there's the whole process. We can see there's pocket emptying and pocket filling going on. Let's just take a look at oxygen deficit and oxygen debt. So what was that pocket emptying? Essentially, we were using two other systems. We were using the ATP-PC system, and we were using the lactic acid system as we were emptying that pocket. So with oxygen deficit, remember, a company runs on a deficit. Deficit, things are happening as we speak. Debt is something that's happened, and now we're in debt. We buy a house, that's done, now we're in debt, and we've got to start paying it off. It's not something that's continuous. So the deficit is happening. What could we say about that? We could say, well, the demand for oxygen is greater than the supply. The heart rate's not up there yet. Yeah. We could say that the aerobic system can't supply the required energy. Yep. We can say that, therefore, the anaerobic systems, that's the ATP, PC, and the lactic acid system, there they are written on the pocket, they meet the shortfall. And that in the final sprint, the deficit is going to increase even more. That's when you're told, come on guys, empty the tank now. This is your last hurrah, let's go for it. Final straight, last 50 meters, dig, and you really finish having emptied the tank, having properly emptied your pocket, depleted your ATP, PC, and your lactic acid system are absolutely done. Oxygen debt, we've bought the house, now we're in debt. We've finished the exercise. Now we need to essentially do two things. We need to restore our systems. We need to the ATP-PC system. So the phosphate and the creatine, we need to restore them, and we need to remove byproducts. Essentially, carbon dioxide and lactic acid need to get removed. And until that happens, our heart rate's going to remain elevated. We are still in oxygen debt. Eventually, though, we're going to get back down to where we were, to normal levels. Oxygen deficit, oxygen debt. What type of questions might we get asked on this? Here we go. 1500 meter runner accelerates at the start of the race until they reach their desired speed. In the final stage, they sprint towards the line. That's that. Come on, empty the tank. After that, they perform an active recovery. Explain oxygen deficit and oxygen debt. What can we say? Exercise begins. In fact, I tell you what, guys, you can pause this. I need to get to that staff meeting. You can pause this and you can read through these and see if we have hit those and see if this is helping you to understand that system. There's another question. Now we're starting to see, look at the bottom there, that's Luigi who's more trained. The more trained, the quickly you'll return to your resting breathing rate and heart rate. This question was about breathing rate. That's why they've put breathing rate in there. And there is another one which might look a bit scary to start with, because it's asking specifically about a trained athlete and an untrained athlete, but you'll see that we can still hit our points there. That was only for 3 points. So there we go. Hopefully that's been useful to you. We will go over these again in class. We've got other stuff, other videos that I've got for you to watch, but hopefully that has been of use to you. I look forward to seeing you very soon. Thank you.